Okay, so today's 7.1, angles and their measures. So first page is all about definition. So when two rays are drawn with a common vertex, they form an angle. We call one ray of an angle the initial side and the other the terminal side, as you see down here on the drawings below. Is your initial side and terminal side. If the rotation of the angle from the initial side to the terminal side is counterclockwise, then the angle is positive. If the rotation of the angle is clockwise, then the angle is negative. Okay. An angle is said to be in standard position if its vertex is at the origin of a rectangular coordinate system and its initial side coincides with the positive x-axis, as you see here on all these pictures. You have the vertex at the origin, and the initial side is always on the positive x-axis. Okay. And positive angles means we go counterclockwise. Negative angles mean we go clockwise. If the angle is in standard position, or when the angle is in standard position, either the terminal angle will lie in a quadrant, theta will lie in quadrants 1, 2, 3, or the terminal side will lie on the x-axis or y-axis. In that case, we call it a quadrant angle. All right, so 90 degrees or negative 90 degrees or 180 degrees and 360 degrees would all be considered quadrant angles because those would lie on an actual x-axis or a y-axis. Okay, so there's our page of definition, going over what angles are. And now we get into degrees. Jessica's dead already. Perfect. All right. The angle formed by rotating the initial side exactly once counterclockwise, one revolution is to measure 360 degrees. So one revolution is 360 degrees, or it is also, let me write here, it is also equal to 2 pi radians. So a revolution is 360 degrees or 2 pi radians. Okay. 1 degree is, of course, 1/360th of a revolution. 90 degrees is a quarter revolution. 180 is half, and 360 is 1 whole revolution. Okay. So down below, we are just going to draw out the angles. Initial side, terminal side, and where do you think 45 degrees belongs? So for this one, we can go ahead and label our quadrants with their angles. So here's 0 degrees. There's 90 degrees, 180 degrees, 270 degrees, and one full rotation, 360 degrees. This means that 45 degrees would be in which quadrant?
1.
Quadrant 1, good. There we go. There's initial, and then 45 degrees would just cut straight through. There's terminal, and this would be 45 degrees.
I have a question.
What's up?
Is there any are there any cases where the initial side or where the initial line would start, somewhere else other than?
If we, if we're not dealing on the rectangular plane, then yeah, it could start anywhere. But
okay, gotcha.
Yeah. Other than that, it's always going to be on the positive x-axis.
Yes, sir.
Yeah. Be different if we were teaching geometry, but we're in trigonometry, right?
I suppose.
All right. And then label these again, 90, 180, 270, and where would negative 90 degrees be?
Well, you'd go clockwise, right?
You go clockwise and end up where?
270, or where the 270 would be.
Good. So there'd be my terminal side, and this would be an actual 90-degree angle, but negative 90 degrees. There you go. So that would be a quadrant angle because it lies
Would-
on the y-axis.
Well, would negative 90
That-
degrees be the same thing as 270, or it's
Yep.
just like,
Yeah, good. So we'll learn something later called coterminal angles. So
Okay.
negative 90 would share the same trigonometric values as 270.
okay, all right, cool.
So just keep that in mind. What was that, Ethan?
I was gonna say, does that change the quadrants when it goes from positive to negative, or no? It's just the same.
Yeah. Okay. 225 degrees. So again, I'll just label it again. 360, 90, 180, and 270. And what quadrant is 225 degrees in?
3.
Well, you go to 180, then add a 45, and so
So
3.
3. There you go. And this would be 225 degrees. All right. Last one, 405. So there's 0. There's 360, 90, 180, and 270. And where would 405 degrees be?
1.
1.
Good, because if we're at 405, that means we went over what?
360 plus 45.
There you go. So
You're just
this
gonna basically
would
start
look,
back over in the rotation again.
exactly. So we'd look
And
like
would
that.
405 degrees share the same value as 45?
Exactly.
Okay, cool.
There you go. And that's how you draw angles. That's not bad, right? Trig is easy.
I think it's actually fun.
It's fun, right? That was good times. Got to use different colors. We got to draw. All right.
Gross.
Any questions on this page?
No.
All right. All right. Next is the definition of a radian. A radian, a central angle is a positive angle whose vertex is at the center of a circle. The rays of a central angle subtend or intersect an arc on the circle. If the radius of the circle is r and the length of the arc intersected by the central angle is r, then the measure of the angle is 1 radian. So in English, if the arc length is equal to the radius, the measure of the central angle is 1 radian. So this is the definition of a radian value. There's also other cool definitions. I put this link on here just to show you how you get a radian as well.
Wait, could you repeat how you summarized it right now?
Oh, sorry. Where did I go? There we go. So it said if the arc length is equal to the radius, the measure of the central angle is 1 radian. Another way to say it is to get the measure of a radian is you take the radius and you wrap it around the circle.
Okay, thank you.
Yep.
I like that better. The other one is too many
Yeah.
big words.
Can I click on that? I don't think so. If you can click on that link, do it. I don't think it's letting me. Do it. Because it actually has the animation of the radius being wrapped around the circle. And it just keeps doing that. Okay, it worked. Go. Oh, it's giving me Internet Explorer. Eel.
Old school,
Right? Let's see if it loads.
huh? Nah.
Math is fun. No. Come on, work. Maybe I just copy and paste it. Copy. There we go. And then I can go to, where's my, there we go. And that, and paste. And let's go. There we go. So look at that. This is how you get 1 radian. Woo! Cool stuff, huh?
Yes, sir.
All right. All right. So with that being said, we come across the formula for arc length. So for a circle of radius r, a central angle of theta radians subtends an arc whose length s is given by the formula s equals r times theta. So if you're wondering what I'm saying right now, this little symbol here is pronounced theta, and it represents an angle in degrees or radians. But when we use the arc length formula, theta must always be in radians. If it's not, then we must convert it. Okay. No, what are you doing? Hang on. Technical difficulty. There we go. So S equals R times theta. So example 1, let's go ahead and try it. Find the length of the arc of a circle of radius 2 meters subtended by a central angle of 0.25 radians. So all this is giving us is a radius at 2 meters, and it's giving us a value of theta at 0.25 radian, and this just wants us to find the arc length. So this is what we're looking at. Here's my circle, and then here is my radius of r. So there's r, here's theta, and what we're looking for is the length of this arc, which is given by S. That's the arc length. So that's everything we're looking for. And they're giving us R and they're giving us theta, which means all we have to do is plug it into the formula.
Isn't it if okay, so like wouldn't it be if it's a radian? Like if the angle is in radians, then wouldn't that make the arc length equivalent to the radius?
Good question, right? So we say that so the radius, so you're able to wrap it around, but that doesn't give you the actual radius, right? So whatever wraps around the circle is what gives you your value of theta. So radian just represents that measure, that angle of measure.
Okay.
Yeah.
Oh, because it's like from how far from the circle. Okay.
Exactly.
Okay, I got you.
Yeah. So radian is just an angle of measure of that. Okay. No, that was a good question. So here, 2 meters times 0.25 radians. Well, that's just what? 0.50 meters, right? And that is the arc length of that circle. What's up?
If we were dealing with like a negative angle, what would change with the radians? Like how would it be negative as well?
Yeah, I mean, we can have negative radians, but in this case, I think since we're dealing with length, length can never be negative. Therefore, that angle could never be negative either.
Okay, thank you.
Yeah.
Wouldn't in that case you just like convert it into like say you got the -90, right? You're looking for that angle or something. Wouldn't you just be able to use the values for 270 rather?
Yeah, that is true. Yeah, because you can convert it to a positive angle and make it work. But we're not there yet. Okay, baby steps. Baby steps. All we're doing here is finding arc length. So for this given circle with a radius of 2 meters and an angle of 0.25 radians, that arc length is 0.5 meters. There we go. Those are valid questions, those. I like it. Okay, so example 2, given that theta is 1/4 radians and S is 6 centimeters, find the value of R. So here we're looking for the radius. So they give us theta as 1/4 radians, and they give us that S is 6 centimeters, and we need to find r. So using the formula, S equals r times theta, well, it's easier to rearrange the formula and then plug in, or if you want to plug in and then rearrange, it doesn't matter. Here, I'm just going to rearrange and solve for r, which means you'll just get S over theta equal to r. And then you'll get 6 centimeters over 1/4 radian equal to r, and 6 over 1/4, you'd multiply by the reciprocal, and what would we get?
24.
There you go. 24 centimeters is equal to r. And you notice how we keep the radian off, because here we're still talking about length. So our length is 24, just 24 centimeters. Okay. Perfect. I think by our radian definition, we're saying no matter what the radius is, as long as you're able to, what is it? I just had it in my head. Whatever the radius is, no matter what, the angle of measure between those same radii are going to be 1 radian. So if that makes any more sense.
Wait, can you repeat that again?
So for our definition above of what a radian is, like an angle of measure, it's basically saying no matter what the radius of an initial side or a terminal side is of an angle, no matter what that radius is, the measure of the angle will always be 1 radian.
So how many degrees is 1 radian?
It is 50, what is it, 54? Something like that. Let me see, 180 over pi. 57.29 degrees is 1 radian. Good questions. Okay.
So if we ever have to convert from degrees to radians, like we have the same problem, but we had to convert it at the end, we would just multiply it by or divide it by that. We said it was a 54.7 or whatever it was.
That's what we're doing next. Look at that. So good. So if we ever have to convert from degrees to radians or radians to degrees, then here is the formula we would use. Well, first we make the ratio, right? So we know that 1 revolution is equal to 2 pi radians or 360 degrees. If you divide that ratio by 2, you get that 180 degrees is equal to pi, which is true. Pi radians is equivalent to 180 degrees. Now, to make a conversion ratio, you can say that to go from degrees to radians, you would multiply by pi over 180. And to go from radians to degrees, you would multiply by 180 over pi, which is all right here. So to convert from degrees to radians, you would take your degrees and multiply it by pi over 180 degrees. And then to convert from radians to degrees, you would take your radian value and multiply it by pi over 180. And a radian is much larger than a degree because it's 57 times larger. So again, 1 radian is equal to, what did I say?
57.6 or 29 or
degrees. There you go. So a radian is definitely bigger than 1 single degree. Crazy, right? Okay, so these are the conversions we will use, again, to go from degrees to radians, radians to degrees. All right, so let's go ahead and try it below. This says convert from degrees to radians.
I have a quick question.
What's that?
About how many do the radians say they if they wrap around the circle, do they always form like a complete circle?
It depends on how many, like, I guess if you're talking about revolutions, right?
Yeah, revolution. Sorry.
Yeah. So, I mean, it all depends on how many revolutions you want to go around the circle. But just know that now that we have an equivalence, we have a ratio that can show us the equivalent radian to an equivalent degree. Just like how 270 was the same as negative 90. Therefore, 270 can be the same as 3 pi over 2 radians. And they will all share the same trigonometric values at that angle.
We need to get there first.
So when we get there, like I said, take it easy today. And all we're doing is converting. We're learning about angles. We're learning about degrees. We're learning about radians. So let's just do this. Okay. So here we have 60 degrees. We want to convert it to radians. So 60, you'll multiply it by pi over 180. And this will give you 60 pi over 180, which will reduce to what? Pi over what?
It should be like 1 something, right?
60 over 180.
One pi over 3.
That's it. Pi over 3. So what we're saying here is that 60 degrees is equivalent to how many radians?
3.
Pi over 3 radians.
Oh, nice.
That's it. So 60 degrees is the same as pi over 3 radians. That's it. Okay. Do it again for 150. Multiply it by pi over 180. This will give you 150 pi over 180. Just reduce the fractions and you'll get what?
3 over 6, or yeah, no. I'm thinking about
Pi over 8, or I don't know if it's 8 or are we
5 pi over 6.
Good. 5 pi over 6 radians. Everybody go with reducing fractions?
Hey, sir.
What's up?
So if we ever want to actually plug in pi, like an actual number value for pi,
Mhm.
like, do we have to use pi like in our calculator, or could we just type in 3.14? Or would that be too big of a error?
No, use pi in your calculator because you want all those extra decimal places.
Okay.
Yeah. So yeah, just don't type in 3.14. Just type pi because you need those extra decimal places that it has. Okay. And then 45 degrees. Do it again. Negative 45 times pi over 180 gives me negative 45 pi over 180. And what do we get?
Negative pi over 4.
There you go. Negative pi over 4. Everybody's like, it was good until I saw these fractions. So all we're doing here again is just making an equivalent statement. All we're saying is that, hey, 60 degrees is the same as pi over 3 radians. 150 degrees is the same as 5 pi over 6 radians. And negative 45 is the same as negative pi over 4 radians. And you can do this with any given degree value. Okay. Any questions on those three? Okay. Then let's go ahead and go the other way. Let's convert from radians to degrees. So this time you will just multiply by 180 over pi. So what you're looking at is pi over 6 times 180 over pi. What's going to happen to your pi's?
They're going to cancel and you're going to reduce, getting 30.
Good. Your pi's are gone. You get 180 over 6 or 30 degrees. So there you go. So now we're saying pi over 6 radians is equivalent to 30 degrees. Okay. Again, 3 pi over 2 times 180 over pi. Your pi's cancel. And then how many times does 2 go into 180?
90.
90 times, right? That becomes a 1. That becomes 90. And 3 times 90 is
270.
270 degrees. So 3 pi over 2 radians is the same as 270 degrees.
So the first step would be cross multiply.
That's it. See? Old school stuff. We could have did that above, but I was just taking it easy. Didn't seem to work though, huh?
Nah, not today.
Brain is trying to wake up still. It's been a week.
From last week. It's still frozen. Understand. Okay. Here, pi's cancel. 4 gives into 180 how many times?
45.
45.
45 times. And negative 3 times 45 is
Negative 135.
negative 135 degrees. Perfect. So that's how you convert from degrees to radians, radians to degrees. So when we deal with arc length, if you're ever given an angle in degrees, it must be converted to radian in order to solve for arc length. And it's going to be the same for the area of a sector, which is next. The area of a sector, your degrees must also be in radians. But any questions on this page before moving on? Okay.
No, but Jessica comments pretty funny. I don't know. Okay. Yep. All right. Next is finding the area of a sector of a circle. So area of a sector. So the area A of the sector of a circle of radius r formed by a central angle of theta radians is given by the formula A equals 1/2 r squared theta, where theta, again, must always be in radians. Okay, so I guess I could draw a picture of what we're finding here. So there's my circle. And then if I have my radius there, and my theta, I'm not going to draw theta. What we're finding here is what the area of this actual sector is. And I'll say theta was right there. Okay. So we're finding the area of your slice of pizza, all right? Okay. So find the area of a sector of radius 2 feet formed by an angle of 30 degrees. So here they give us the radius in 2 feet. They give us our theta as 30 degrees, but what's wrong with that?
We have to convert.
Non-radians.
It's okay, good. We have to convert it to radians. So you multiply by pi over 180, and what do we get?
Pi over 6.
Good. Pi over 6 radians. Okay. Well, we have all the information we need, which means we can find the area just by plugging in the radius and theta. So you get 2 feet squared times pi
over 6 radians. And then just calculate 1/2 times 4 square feet times pi over 6 radians. And that'll give me 2 square feet times pi over 6. And we're just looking at basically 2 times pi over 6, which is going to give me what?
Pi over 3.
Over 3.
Good. Pi over 3 square feet. That is the area of that sector. If you wanted decimal, you would just do pi divide 3. And I get 1.0, I'll round to 2, 1.0 square feet. Okay, all good?
So when we do these problems, is the unit of measure, like the foot squared, is that going to be a big thing that we're going to have to always, like,
Yeah, I mean,
in mind?
you either my math lab gives it to you or you have to type it in. I'm assuming it gives it to you, but yes, always keep units in mind, because then let's say you're doing your work and you leave the unit off and you're like, hey, I need 1.05, what? You send somebody to Home Depot, like, come me 1.05 feet, centimeters, right? So just always be proper and keep that unit of measure on. All right, not bad. Okay. And now, 2, given that r is 6 meters and the area is 8 square meters, find the value of theta. So I'm just going to rewrite the formula here. A equals 1/2 r squared theta. And they're asking us to solve for theta, giving us the radius and the area. So I like to rearrange these formulas just to solve for the piece I don't know already. So we're going to solve this for theta. So I'm just going to rearrange. So I'll get rid of that 1/2 just by dividing it, which will give me 2a on the left equal to r squared theta. And then just divide by r squared, and you get 2a over r squared equals theta. So we just rearrange the area of a sector formula, and this is the new formula for theta, which means that all we have to do now is plug in everything that we know. So theta is going to be 2 times 8 square meters over 6 meters squared. So what we end up with is 16 square meters over 36 square meters, where this is important for units. Your units will what?
Cancel.
Cancel. And what does 16 over 36 reduce to?
4 over 9.
4 over 9 radians.
I have a question. I might have just missed it, but where did the squared on the 8 come from?
That is from what's given.
Okay, sorry, I didn't
Right.
see that.
You good. 8 square meters. All right. Or 0.44 repeating radians. Okay. That's the area of a sector. All right. Any questions on that page? All right, then. All right.
right, next page. We get into linear speed and angular speed. So for linear speed, suppose that an object moves on a circle of radius r at a constant speed. If s is the distance traveled in time t on the circle, then the linear speed v of the object is defined as v equals s over t. So for our linear speed, if we're going around a circle, it's how s is the distance of how far we traveled over time t. So maybe I could draw a picture of that. Let's see. Let's just do that. And let's say that we just traveled around. I'll put it there. And this is going to be S. And we calculate how far we traveled, S over the amount of time T. That's it. That's linear speed. So however far you traveled across the circle over a certain amount of time. Okay. And the next is angular speed. The angular speed omega, right? Fancy W, omega of this object is the angle theta in radians swept out divided by the elapsed time. So now this time we're traveling around the circle, but we're only worried about how much of an angle has been swept out over time. So what would be another good picture of this? Let's see. Let's say we start here and then we travel. So let's say we travel around the circle. Let's say we stop here. That's too straight. Let's say we stop there. That's perfect. Give a little more of an angle. So what we're looking at is at how much of an angle was swept out. So that'll be our theta over again in amount t. So for angular speed, it just wants to know how many radians have we swept out as we have traveled around this circle. Okay, so those are two formulas for linear speed, angular speed, and now we have a third formula, which is an important relationship between linear and angular speed. Okay, so we only use this formula if the question states something in radians per unit of time, and you will see it in the actual problem. So for this third equation, we take the linear speed equation, v equals s over t, and we input the actual formula for s. Remember that s was the formula for arc length. S was r times theta, which found the arc length of a circle. So we plug in r times theta over t, and then we separate it into r times theta over t. Well, it just so happens that theta over t is the formula for angular speed, omega. So we get this new formula of v equals r times omega. And we only use this when we see in the problem that we are revolving over a unit of time, radians per unit of time. So if the angular speed is given in terms of revolutions per time, be sure to convert it to radians per unit of time, noting that 2 pi is equal to 1 revolution. So if our problem gave us that we were revolving 900 revolutions per minute, we would want to convert it to radians per unit of time by multiplying it by 2 pi radians over 1 revolution, giving us 1800 pi radians per minute. But again, you only use the third formula if you see that the problem's giving you a certain number of revolutions per unit of time. And I think it's stated pretty clearly in the problems, as in the next one. So, a child is spinning a rock at the end of a 2-foot rope. at the rate of 180 revolutions per minute. There it is. There's your keywords that tell us that we get to use the third formula above. Find the linear speed of the rock when it is released. Now, what parents let their kids spin a rock on a rope?
I was just thinking that myself.
Good parents.
Like, here, go play with this rock.
He's pretty skilled.
All right. So let's go ahead and find the linear speed of this. Oh, when it's released. So this kid's going to release the rock. It's always a good problem. Okay. So like I said, since it has the revolutions per unit of time, we get to use this formula. V equals R times omega. Well, there's one thing we know. What is the radius?
2 feet.
2.
2 feet. Good. Then, in order to find omega, we need to convert 180 revolutions per minute into radians per minute. So all we have to do is multiply this by 2 pi radians over 1 revolution. Hey, conversion tables. You guys seen those before?
Love them.
Been a long time, right?
So can you kind of explain why we are multiplying by 2 pi radians?
Because since we're trying to find omega, since this kid's spinning the rock out, we want to know how much of an angle has been swept out as this kid's rotating the rock.
At 180 degrees, or
And in order to do that,
like
you need to convert it. You need to convert it to radians per minute. So it's because when we convert it to radians per minute, it's telling us how much of an angle is being swept out per unit of time.
and 2 pi is equal to 1 revolution.
One
right?
revolution, exactly. So this is why we have to convert it. Okay, so your revolutions will cancel. Your unit of revolutions will cancel. And we'll get 180 times 2, which will give me what?
360.
360 pi radians per minute. So this kid is now spinning his rock at 360 pi radians per minute. Just sounds crazy, right? Okay.
That could spin that fast.
So next, all we have to do is plug in what we know. 2 feet times 360 pi radians per minute. And 2 times 360 gives me what?
720.
720 pi. And now our units are going to change a bit. This kid's spinning the rock. The linear speed is 720 pi feet per minute. Okay.
Why did it change from radians to feet?
Because radians is giving us a measure. So we already found out how much of an angle is being swept out. And now all we are really worried about is linear speed. We want to know how fast this rock is traveling. So now that angle unit of measure no longer matters. But since we're in America, do we know how fast 720 pi feet per minute is?
Sure.
No, because we like to convert everything to what? You drive in feet per minute, or you drive in what?
Miles per hour.
Miles per hour. So let's see how fast this kid is actually spinning the rock. And we're going to set up another conversion table. Watch this. We're going to say 720 pi feet per minute. And let's convert to miles per hour. Well, how many feet are in 1 mile?
5,280.
5,280. Thanks, Googles.
Oh no.
I'm just kidding. And then, how many minutes are in 1 hour?
60.
60. Look at that. You guys have to have seen conversion tables somewhere.
Yeah, I saw him in chemistry and hated it. I
There
thought
you go.
math, I wouldn't have to do this in our math class.
So feet cancel, minutes cancel, and now we'll be in the appropriate American measure of miles per hour. So all we have to do now is multiply 720 pi times 60 and divide it by what?
5280.
5280. There you go. I'll write that down here. 720 pi times 60 over 5280. And let's see how fast this kid's actually spinning this rock when he releases it.
So, never mind.
What you got?
This is more just like, why don't you have to also do, like divide by 24 because there's 24 hours in a day or something like that. Like, I don't know. Conversions always confuse me for some reason.
Gotcha. Well, if we wanted to know how fast he was spinning it in days, we could. But
Let's do it.
we don't need to.
Never ending.
Because we know we just wanted to put it into hours, so we know we can go from minutes to hours, right? We can find any rate we want. We could have said, hey, let's change this into miles per second, right? Or let's just change it into feet per second. We know how to make those conversions. But now, who's got the number? How fast are we spinning this rock?
25.7039398.
All right. You think that'll hurt somebody if it hits them?
Knock them out.
Oh yeah.
Why don't we, do an experiment? Let's see.
Meet me at my house right now.
What if the rope snapped?
Knock that
That's
out.
part of the experiment.
Okay, excellent. So again, the third formula is special because it only matters when you have revolutions per unit of time.
And you said like any question where it says revolutions per minute, we know that we're looking for that, right?
Exactly. So if you ever have revolutions per some type of unit of time, per hour, per minute, per second, you will use that third formula of R times omega.
Okay, thanks.
Are we gonna need to convert it to miles per hour for like my math lab? Or
I think so. That's why I show it. I think it makes you do it.
That's
you could've-
heartbreaking.
We could have did just 720 times pi, and that was spinning at, it sounds a lot faster. This is 2,261.95 feet per minute. Now that sounds dangerous.
Deadly.
But we need to put it into our terms. Unless you live in, who does kilometers? I think it's Arizona, right?
Really?
I think so. All their signs have kilometers, I think. It's been a while since I drove through there, though.
That's weird. I thought the whole US, that was like the standard like US way of doing it.
No, some of them will have kilometers. I'm like, what's going on here?
I think it's because we're trying to convert, like not use the metric system anymore.
Yeah, we want to be better
Oh,
than
yeah,
the
let's-
metric
let's-
system. All right.
My brain will be out the drains if they do.
Mm-hmm.
And well, for miles per hour, wouldn't we convert down to like 25 miles per, or wouldn't we
Just round it or what?
round it down to 25 miles per hour? Because, you know.
We're scientists right now. Keep those decimals.
You're right.
Add 4 more decimals. Yeah, I can't wait for the day for a cop to pull me over and be like, "You were going 25.7 miles per hour. You got that point
actually
7."
going 2,200.
Okay. These are the last 2 questions. So you guys take a moment, try to work on them, and then I'll jump in probably about 5 to 10 minutes. Let me stop recording too. Okay. Windshield wipers are the worst, aren't they?
Seems like it.
So we want to find how much the 24-inch blade cleans. So the first thing we want to do is convert that angle of 125 degrees to radians. And then next, we want to know what area the whole wiper blade covers. So that's what I did for area 1 in purple. So the 30-inch blade covers 981 square inches on the windshield. And we all know how windshield wipers work. The 6-inch arm is the part of the wiper that does not clean the windshield. So I get the area that's not clean, and I subtract it from the area that the whole wiper blade covers, and that will give me the actual area that the 24-inch blade cleans.
I know the numbers don't add up, but why is it you couldn't just like put 24 into it?
Because if you put 24, you're assuming that the wiper blade length is 24 and not 30. So if you're just typing in 24, it's not going to give you this area exactly. It's going to give you the area that a 24-inch blade would clean, but not the actual area that we're looking for. Because if you put 24, you'll get 628 square inches, which is not true.
So 24 is really not like a factor in the problem, really.
No. So again, you take the whole length of the wiper blade and you subtract it from the area that it's not covering. And that'll give you the area that the blade is actually cleaning. And all of that was area 1. No. Oh, I don't need to highlight that. Okay. Okay. What are the questions on that one? Like wiper blades are the worst. Okay. Move to the next one then. An object is traveling on a circle with a radius of 5 centimeters. If in 20 seconds a central angle of 1/3 radian is swept out, what is the angular speed of the object? And what is the linear speed? Okay. So let's see, where's my formulas? There we go. Okay. I'm going to write down what they're giving us. They're giving us a radius of 5 centimeters. They're giving us time, which is 20 seconds. And they're also giving us an angle of theta of 1/3 radians. So the first thing we can find is the actual angular speed. So angular speed is given by the formula omega equals theta over time. And theta
is 1/3 radians over the unit of time, 20 seconds. And 1/3 over 20 gives me what?
(1/60).
Good. This will give us 1/60 radians per second. No, stop it. Okay, there's that. And then linear speed is just going to be the formula V equals S over T. Well, we don't know what S is, but we do know the formula for S, because remember that S represents the formula for arc length. So this can be rewritten as R times theta over T, where now we know the radius, the value of theta, and time. So you'll get 5 centimeters times 1/3 radian over 20 seconds. And then 5 times 1/3 over 20, we get 1/12 centimeters per second. There we go. All right. So, any questions on those two?
So could you, instead of doing that, could you have just plugged in V equals RW?
No, because we were not given the words revolutions per unit of time.
You pretty much have to solve for both of them.
Exactly. Oh, I see what you're saying. R times omega, right? But it's not a revolutions per time.
Well, because when you do the math, it still comes up to 5
Because
times
if you-
1/60th.
Because if you did R times omega, you might be right. It's a nice shortcut. You get 5 times, because we found out what omega was, right?
Yeah.
Hey, yeah, because 5 times 160, yeah, you would get 1/12. Hey, so that works too. But it wasn't for that problem.
I can't ever be right.
Yeah, it's right. It's good. I mean, that's why they have that special relationship. So
it doesn't matter the problem as long as you find.
good thinking. Yeah, but I mean, let's just say that it just said find linear speed and there was no angular involved, then you couldn't use that. So if it just had regular or linear and it gave you S and T, then you wouldn't be able to use the R times omega. Okay, not bad. All right, what other questions? Okay, then let's just move on to the last page. So here is gonna be your best friend the rest of the semester, the unit circle. Yes, you can Google one and have it already, but what's the fun in that? We are gonna learn how to fill out the unit circle throughout chapter 7. Today, like I said, we start slow. The only thing we're gonna do today
is fill out the degrees and the radians. And I listed that table right below in case you needed to follow along. So I'll start it off. And actually, I'll focus on the first quadrant first. This is going to be 0 degrees and 0 radians. And then if you follow that table below, we next go to 30 degrees and pi over 6 radians. And then we go to 45 degrees and pi over 4 radians. Then we go to 60 degrees and pi over 3 radians. And then we go to 90 degrees and pi over 2 radians. And then just keep following it from there. And then we go to 120 degrees and you get 2 pi over 3. And then we go to 135 degrees and you get 3 pi over 4. And then we go to 150 degrees, which is going to be 5 pi over 6. And then we go to 180 degrees, which is pi radians. All right. So we are seeing where these angles live on the unit circle, and just by filling that out. And then after that, it's 210 degrees. And we're going to have, what is that? 2 pi over 6, 5 pi over 6. I think that's 4 pi over 3, right? Or am I mixing that up? It's either 4 pi over 3 or 7 pi over 6. That's going to be 7 pi over 6.
Yeah, I think it's 7 pi over 6.
7 pi over 6. Okay. And then 225, you're going to get 5 pi over 4. And then 240. There's my 4 pi over 3. And then 270. There's my 3 pi over 2. And then 300. And this one's going to be my 5 pi over 3. And 315. That's going to be 5 pi over 7 pi over 4. And then 330. That's going to be my 11 pi over 6. And then we get to 360 and 2 pi radians. Yeehaw. And that is the beginning of our unit circle, guys.
Can we reference this like for any like problem? Like, will these values ever change?
Nope, they'll never change. These are set in stone ever since they were created, so they'll never change.
Okay.
And
So
go ahead.
you mentioned that if we know one quadrant, we can figure out any quadrant. What is like the
Exactly.
little shortcut to that?
Exactly. So once we figure out these coordinates, I think that's, like I said, in 7.3 or 7.4, you can start memorizing. But again, you see that the unit circle is very symmetric. So you can reflect these across. Here's pi over 6. If you reflect it across, you're there, 5 pi over 6. If you reflect it over, there's 7 pi over 6. If you reflect it over again, there's 11 pi over 6. So again, if you just know where pi over 6, pi over 4, pi over 3 are, then you can reflect those over to find the rest of them.
That makes it so much simpler.
So crazy, right? However you can memorize it. You can even Google the hand trick. You're like, your pinky is 0, 0. Then your other finger is pi over 6. And then your middle finger is pi over 4. Your pointer finger is pi over 3. And your thumb's pi over 2. Unit circle on one hand. and just reflect it. Just slap yourself until you get it.
So basically, like, just memorize the absolute crap out of this.
If you know the first quadrant, you know the rest, because even the points are going to be symmetric. Like, let's say that this point here was, let's just say it was 2, 2, right? If you reflect it over, it's going to be negative 2, 2. If you reflect it under, it's going to be negative 2, negative 2. If you reflect it over there, it's going to be 2, negative 2. Those aren't the correct points, but I'm just showing you how it works, how symmetric the unit circle actually is. Crazy, right?
So when you say reflected, I get how you how the degrees,
Mm-hmm.
because you just gotta do it by like 180 or whatever, or by 90 depending on the quadrants.
Mm-hmm.
But the radians, is there an easier way to like that?
I like to figure out where the radians are. Think of a watch, a clock. You can actually count radians like you can count on a clock. So let's just say I want to find where all the pi over 6s are, right? So I'll start at 0, and then I'll add a pi over 6. And 0 plus pi over 6 gives me pi over 6.
So we're
Now
going
let's say,
counterclockwise.
what's that?
So we're gonna go
And
counterclockwise.
and we're always going to go counterclockwise unless we want to go negative. And you can do the same method going negative as well. So if I was going negative, I would subtract a pi over 6, and this would actually be negative pi over 6 instead of 11 pi over 6. But you can count radians like a clock. So again, 0, then I say pi over 6. I want to find the next pi over 6. So I would add a pi over 6 to my other pi over 6. That would give me 2 pi over 6, which would actually reduce to what?
Pi over 3.
Pi over 3. And I'd be here. And then I'd add another pi over 6. So I'll just add it to all these, right? Pi over 6 plus pi over 6 plus pi over 6 gives me 3 pi over 6, which means I would be where?
Pi over 2, 180.
At pi over 2. And then I'll add another pi over 6, and I'd be at 4 pi over 6, which would be where?
2 pi over 3.
2 pi. See? So that's how you count radians. And then if I added another pi over 6, I'd be at 5 pi over 6, which is there. Crazy, right? And you can do that with any radian value. Pi over 4s, pi over 3s, pi over 2s, pi over 15s, pi over 20s, whatever. If you want to know exactly where it's at, just count it like a clock. Just keep adding pi over 6s or whatever you're dealing with.
Everyone's having an epiphany, and I'm getting more confused. I think I'll just stick to the converting degrees to radians.
That works too. Like, let's say, like, all right, find this. It's at 370 degrees. One of the easiest ways to do it, or actually, let's say it's like, it gives you like, oh, here's 64 pi over 90. You can convert that to degrees to find exactly where it is, which is another easier way to get out of it. And that's all coming, don't worry. Yeah, but you can count radians like a clock. That's all you have to do. Just keep adding them up.
And radians are always going to stay in the same spot, right?
These angles are not going anywhere, guys. They're not going to move on you, trust me.